Okay. That's working okay? Hear me okay? Cool. Okay, so my name's Luke Jennings. I'm from MWR in the UK, and I'm here to talk to you about group policy hijacking attacks on Windows networks. Now, for those of you that have read the summary of this on the program, that was written prior to last month. Many of you may be aware that Microsoft released some patches last month, and there was a bit of a media coverage on them with regard to these issues. So this talk now will kind of take two perspectives. We'll kind of look at how I discovered those issues, what led up to that, and then we'll do a little bit at the end looking at what's happened since the patches last month and what's changed as a result of that. So we'll look at a few different areas. We'll do a very brief introductory phase about group policy and how it works. We'll kind of consider the two viewpoints, pre-patch and post-patch. And then we'll look at the different attack scenarios, basically, and the different configuration scenarios that apply, and have a look at what the exploits are. So, very briefly, what is group policy? I'm sure many of you are very familiar with it, but essentially it's a way of managing all your kind of Windows endpoints, managing their configuration, and doing that in a hierarchical fashion. And it's just very powerful, gives you a lot of flexible control. It's probably one of the main reasons, along with something like Office, that Microsoft is still so dominant in the business market. It's extremely useful as a large business, very flexible. A lot of redundancy, can handle multiple physical sites and logical groupings. And it's also very key for enforcing lots of security critical configuration settings across your enterprise. So, how does it work? We're considering a very high-level view here of what's relevant to this talk, really. But there's kind of four key components we'll consider here, really. There's the initial step of using DNS. So if you've got a domain member talking to a domain controller, you'd use DNS. The domain member would try and find out, which domain controller do I speak to via DNS. You'll then have RPC connections involved, at which point it'll then eventually move on to using LDAP as a way of figuring out which group policy objects should apply to it. And then finally, generally, you would move on to SMB as being a method for actually getting the sort of low-level settings, so the full group policy configuration content. So, one other thing to consider here that's important, we'll come to later, is client-side extensions. So, there are lots of different configuration settings that you can configure in group policy. Only a small number of them generally apply by default, but depending on what you configure, it may enable separate client-side extensions. So there are some for security settings, some for registry settings, some for user management and group management on endpoints, even the Internet Explorer zones. There's quite a lot of them, but they won't necessarily apply by default unless you've, as an administrator, configured a setting that falls into that category. Most of them, though, at the end of the day, they tend to end up as being a registry change on the endpoint. Not all of them, obviously, for user accounts and so forth, that differs slightly, but most things tend to be to end up as registry changes. But you've got file changes as well to consider, and user and group changes. So I mentioned before, we'll consider the scenario pre-patch. So say I reported the things I found back in March. And then last month, February Patch Tuesday, we had MS15011 and MS15014 come out that relate to these issues. So we'll mostly consider the pre-patch scenario first, and the things that I did that led to that, led to these findings. And at the end of that, we'll kind of look at what's changed since these patches came into play and how effective they are. So, how can it be attacked? There's a few important considerations to make here. So, first of all, each stage has to complete successfully. Obviously, if it fails to look up a domain controller in DNS, it's not going to carry on with the additional steps. But likewise, if it fails at the LDAP stage, for example, and it doesn't know what GPOs it's supposed to apply, it's not going to then go on and just try and connect to SMB and apply settings anyway. So that's something that's very important for us to consider going forwards. But beyond that, pretty much, at the very least, if you can end up controlling the low-level settings with group policy, they're powerful enough that pretty much if you control those, you control all the endpoints under them. And even just at the LDAP level, the high-level kind of configuration of which DPOs should apply or should not apply, that potentially could end up through a sort of stage attack being the same thing. But put simply, it's pretty powerful technology. So if you can control those settings, then that's pretty bad. So what are the main kind of threat scenarios we're kind of considering here? Well, I mean, first of all, at the DNS level, we're just looking at redirecting communications effectively. If we can modify that on the DNS server or at the transport layer, then we can redirect requests to a malicious server pretending to be a domain controller, for example. But we've got sort of access control on DNS writing. We may not have transport protection, but unless we've got DNSSEC, but that's not necessarily that relevant at this stage because the key security mechanisms come in at the later stages. So second stage, we've got RPC. That has authentication associated and a secure transport channel. We move on to LDAP. We've got LDAP authentication, LDAP signing as the security controls there. And at SMB, where we'd be actually modifying the low-level group policy settings if we were exploiting it, then we've got SMB authentication and we've got SMB signing. So let's have a look at a few relevant configuration details. So first of all, we'll look at domain controllers. So this is the default domain controllers policy that would be applied ordinarily. So one interesting thing highlighted there is with relate to LDAP. The default configuration, at least as it in that setting template, is not to have any requirements over signing for LDAP. We're actually going to kind of leave that for now. We'll come back to that much later. But for now, we're going to focus on the SMB components of it. So if we look there, we've got and the RPC, so we've got for the domain member digitally encrypts and sign secure channel data. That's required. That's enabled always. And the Microsoft Network Server, which is for SMB communications, we've got digitally signed communications always as enabled. So from that perspective, the domain controller configuration by default is secure, so to speak. But if we come and have a look at the default local configuration, and this is what's going to be default on a domain member, we've got digitally signed communications always disabled, and it's just the if the server agrees setting that's enabled. And pretty much that means that it'll negotiate signing, but it doesn't, at the client side, it doesn't require it. So, one relevant thing I found when I was initially looking into this was actually a TechNet article from Microsoft back in 2010 that was discussing some of the features of SMB signing. And it made this statement that's highlighted there, which was pretty much indicating that the reason that signing is enforced on domain controllers is for this very reason. It's to make sure that group policy data getting delivered to clients has its integrity protected, because that's key, that's security critical. So what scenarios apply here? We've got clients not necessarily requiring it, but servers requiring it. So if you try and tamper with the SMB communications as is, you kind of got one of two scenarios. You either allow the signing to be negotiated, and the connection goes on fine, but then unless you know the keys, you can't tamper with that data, which is obviously what's intended from a security perspective. Or otherwise, you could prevent the signing from being negotiated, and the client won't care. The client will carry on connecting, but the server at that point is going to terminate the connection because it requires signing. So, I mean, initially you might think, okay, well, we're out of luck, but that's not really the relevant point here. We don't have to involve the SMB server at all, really. It's going to live on the domain controller, but we don't necessarily need to involve it in that particular service. So what we could do is we could allow DNS traffic to go through, RPC traffic to go through, LDAP traffic to go through, all go fine to the domain controller. This is assuming we're acting as a man in the middle here, for clarification. But then when it comes to the actual SMB traffic itself, we could redirect that specifically to our own malicious SMB server, perhaps using some NATing rules, for example. And by doing that, the real SMB server, so to speak, is never actually involved. And so we can force SMB signing to be disabled. The client's not going to care. The client's going to carry on connecting and grab the settings. And because the real server's not involved, there's no termination of the connection going on. And effectively, we are then able to control what we deliver to the endpoint. So, just a diagram sort of summarizing that. We're letting everything else go through normally if we're intercepting this traffic, but the SMB traffic specifically, we redirect locally to our own SMB server and don't allow that to go through to the domain controller. So ARP spoofing is obviously a common way of doing a man-in-the-middle. You could do other techniques, but just considering that scenario, for example, here, if you're on a local subnet with a bunch of other domain members. So, okay, I mean, it's a nice concept in theory, but in terms of practical exploitation, how useful is this to us? Does it work? Now, I mentioned client-side extensions before. So the important point here is that only client-side extensions that are actually in use for relevant GPOs and indicated to be so via LDAP will be applied. Additionally, in general, group policy will only be forcibly applied when a new update is made to group policy, and that's also generally indicated by LDAP as well. And so it may not even update unless an administrator has made a change, which kind of puts significant constraints on the timing window of when we can do this. But ideally, to make this most viable for us, we want to rely on default extensions that we know are always going to be applied. Now, security settings are an example of that. Security settings are always configured. That client-side extension always applies. And also, quite handily, they are forcibly reapplied periodically, regardless of whether there's been an update to group policy or not. I mean, it's about every 14 hours, I believe, from memory, but they are forcibly reapplied. And effectively, the way that's implemented is just through a kind of list of registry settings to enforce or change. So if we can control that, we know it's always going to be applied in the default case, and it would effectively give us full control over the registry. Now, okay, so even if we could do that, how do we actually get a shell? There's many potential ways we could consider to do this with registry changes. We might be able to define new services or new run keys. The method that I looked into just because I knew that it had no other dependencies was app init DLL. So, you know, if I define a new run key, I need the system to restart. Whereas with app init DLLs, they'll get loaded into any new process that gets started, and pretty much eventually that will happen even on an active server just through background processes and so forth. The idea here is that you would reference a DLL on your own SMB server, and then next time a process is started, it'll load that DLL, and you'll get a connect back for that shell. One particularly easy way of triggering this normally would be to use an R desktop client just to connect to the system, assuming it's running RDP. That creates a new login session running the system, which will obviously load that DLL and cause a connect back. So that's something generally, in most cases, you'll probably be able to trigger immediately if the exploit has worked. So, to avoid some duplication, I'm not going to demo this right now. We'll move on to another configuration, and we'll come back to this. But for now, just trust me, this works. So, the summary there is that, okay, the default configuration in principle is vulnerable. That's effectively what became MS15011. My original assumption was that, you know, Microsoft may have responded to that by saying, okay, you know, fair enough, that's a default configuration, that's vulnerable, but it's perfectly possible to change the settings and have a more secure configuration. So then I began looking into what would be the case then. So let's assume a maximum security configuration for SMB. So on all endpoints, we've got SMB signing required. So when looking into this, I actually found a way of kind of, to some extent, using it against itself. what I found was that if I was to let all the communications go through as normal, and I wait until the security settings file is being fetched from the first group policy object, if I corrupt the communications at the right point then, causing the application to fail, that obviously the group policy update fails, there's an error in the event log and so forth. SMB sign-in fails, that's detected by the client, the connection is terminated and so forth. I assumed, though, that the impact of that would just be that group policy, or whatever the configuration at the time is, just remains the same because it's not applied anything new. It's failed to apply anything else. But that wasn't the case. What I found was that the security settings then revert to their default local configuration, which is exactly what we saw previously with SMB signing not being required. At which point you're in a negotiate-only standpoint again, which means the original attack we discussed previously then applies effectively as a second stage. And so even in that environment, theoretically, we can still get system. So if we were to exploit a system even in a more secure configuration like this, what's the exploit process? So there's a whole bunch of things we need to consider here. So first of all, we've got to intercept the traffic. So for example, maybe we ARP spoof the member in the DC. And then we need to allow the relevant traffic to go through and forward it. So we allow all the DNS traffic to go through, we allow the RPC traffic to go through, allow the LDAP traffic to go through, and finally, we allow the SMB traffic to go through as well. But when we detect that those security settings are coming back from the domain controller, that's when we take our first action. We deliberately corrupt that response. We cause the SMB signing to fail, at which point the requirement for it on the domain member reverts back to default, which is negotiate. At that point, we modify our IP tables NATing rules, for example, and we make sure that any future SMB communications then get redirected locally to our own SMB server, and then effectively the previous attack applies on the next group policy refresh. So, demo time. So, some of this may be a little bit difficult to see, but this is effectively a Windows 7 domain member. And we're looking at the moment, we can just see that the relevant registry setting, which is the required security signature setting, is actually set to 1, which means that SMB signing is required. It's not negotiated, it's fully required. So we've got the more secure configuration here. We'll then move to our Linux server, and we'll start setting up the exploit. So originally we're going to start with our ARP spoofing. We're then going to run our exploit script, which is starting our local Samba server and a few other redirectors and for sort of SMB communications. And then it's just waiting. So at a certain point, hopefully those settings should come back. It should detect that, and it should corrupt the response. Okay, so at that point, it's found the string it was looking for, it's corrupted it, and then it's changed the IP table rules to forward the SMB communications in future to the local SMB server. So we just have a look here, we can see where that happened, and eventually the connection was terminated at the end. That's just a Y-sharp trace running, showing that going on. So we refresh our setting here now on our domain member, we can see that's gone back to 0. So now we're in the negotiate phase. So we'll go back to our Linux server now and just watch the traffic. And we've got our handler waiting. We'll see at a certain point we should get a new refresh come through, and we should see all the group policy settings being fetched. Okay, so it looks like it's starting to happen there. At which point we should be able to go back to our handler. Now there's no shells at the moment because nothing's been triggered, but if we just fire up our desktop, we don't need to log in, but it just creates that new when login session. Go back to our handler, and we'll see a couple of sessions coming back there. And there, we've got a couple of system shells waiting. Okay, so that's kind of 2 vulns exploited in one video, so that's that scenario configured. So At that point, I kind of thought, okay, maybe Microsoft will say, all right, the first thing you just need to make improve your own configuration. We've got settings you can configure for that. In the second instance, I thought that's definitely a bug. I'm sure they'll probably say, okay, fair enough, we need to fix that, which they did, which is what effectively resulted in MS15014. So then I started thinking, are there any more issues at play here? Is there any other scenarios I'm not considering? So one thing I've kind of glossed over previously is that group policy, it's divided into kind of two key types of settings. You've got machine level settings, which is pretty much what we've been considering up until now. You've then also got user level settings, which apply to the actual relevant user account that's logging into that system at that time. Now, if you've got SMB signing being enforced and NTLM, for example, is being used as the authentication mechanism, which is what we've been kind of doing up until now, SMB signing uses a password-derived key. So I think it's actually it's the NTLM of the user's password done twice, effectively. Now, the interesting thing I found here is that for the machine level settings, the actual machine account for the domain member is what's used, as I would well, that's what I expected anyway, and that's what it turned out to be. But when I looked at the user settings getting applied for when a user logs in, I found that Windows actually uses the user's account rather than the machine account, which is interesting. So the things to consider here is that, at least by default, a machine account, secure, randomly generated password, unless someone's gone out of their way to set it to something weak, by default we assume that account is good. It's not something someone would be able to crack. There's no real easy avenues to get a hold of it without already having system on the box in question. But now, for a user account, that might be a weak password. So it could even be our own account, our own low-privileged domain account, for example, or it could just be some other random user on the network or a couple of users that we've found out their passwords through some means. But the key point to consider here is that if we know a user's password, then we know how to make SMB signing check out, at least for NTLM authentication, when it's fetching user settings. And therefore, in that particular situation, we can control user-level group policy. So the key thought I had at this point is, well, what's the impact of that? Is there an impact? We need to know a password to exploit this, so does that mean anything? Intuitively, my original assumption would have been, well, it probably doesn't change much. I mean, if we've got a user's password, whether it's our own account or someone else's, we've got access to everything they have access to anyway. What does it mean being able to change the user settings applied to them? But on more investigation, what I realized is that the user settings actually have some settings that you can configure that allow a machine-level control. So they might be user settings, but you can define settings that will make changes to the registry local machine hive rather than just the user's registry hive. You can even configure extensions that will add user accounts to the system via the user settings interface, so that it's much more powerful than that. So that means, in principle, if we've got a low-privileged domain user account logging into a system that we know the domain, we know the password for, and we can intercept the traffic to that system, then we can use that as a mechanism to get system on that particular box in the same kind of manner that we did previously. Now, probably the two main situations to consider where this might be useful is that either it's, we've got a low privileged account ourselves, legitimately perhaps, and we're able to log into systems and we want to escalate our privileges, and it becomes a kind of generic way of performing local privilege escalation. Or it could be that maybe there's a few users on the same subnet as us that got weak passwords. Maybe we don't care about those users in particular, but we quite fancy having system on the boxes that they log into. That'd be particularly useful in, say, a hot desk environment where over a period of time they keep logging into different boxes, and we eventually get more and more control over the endpoints there. So, I'm sure there's probably more situations you could consider, but there are two basic scenarios for that. So we'll look into a demo for this one at this point. So just as before, we've got our local configuration set to require SMB signing. So this is a secure configuration. Now, just showing you that the user I'm logged in at the moment is low privileged. Can't create a new user account. It's a low privileged domain account. So at this point, we'll go back to our attacker machine, the Linux VM. So we've got some IP table rules defined there, and now we'll start our ARP spoofing. Now what's happening is that's effectively redirecting comms to our own local SMB server as before, and we've added a user account with the same password to that SMB server. So if the system connects to it, it's going to be able to calculate the SMB signing fine because it knows that user, knows the password, and knows how to generate the SMB signature key for that in that case. So what we'll do now is we'll just run GP update and say, please update the user settings for me. And we'll go back to our machine. Sorry, we'll look at the settings in the registry. So we'll just have a look at the app init settings in regedit here, and we'll see there's nothing at the moment. So just running it again, we refresh, and we see that's now been modified to reference our own DLL on the system. So if we go back to the attacker's machine, we've got no shells at the moment, but we'll use the same trick as before with our desktop to trigger the win logon session to run a system. And then again, similar to what we did previously, we have a couple of system shells that have just popped back. Okay, so that's kind of three different bugs really we've seen. So that's how things were prior to last month. Then Patch Tuesday, February, MS15011 and MS15014 came out. Now, MS15011, it wasn't a patch as such. It introduced a new security control that's configurable via group policy itself. And that's hardened UNC paths. So I think actually there are a few other exploit avenues that I hadn't considered myself previously that Microsoft realized with this, and the idea of hardened UNC paths was a more sophisticated way of controlling this behavior, and it's a pretty cool control. But pretty much what it means is that you can now specify a particular UNC path and even put wildcards in there, and say, you know, if anything matches this UNC path, then you have to use a provider that conforms to these security requirements. And that can be mutual authentication, integrity protection, and even privacy protection if you want confidentiality protected as well. Now we'll see for group policy, our key concern is integrity really, and mutual authentication. Confidentiality is much less of a concern. Now Microsoft recommend the following configuration themselves. It's important to know at this point that's not default. So if you have applied the patches but haven't made any changes to the configuration yourself, then you're vulnerable in the same way you would have been prior to last month. But these particular settings are effectively saying any system you access, if it's a net logon share or a sysvol share, make sure you mutually authenticate the system and you provide integrity protection. Then we've got MS15014, and that is more of a bug fix. So that prevents the reversion to default security settings we saw earlier when there's a failure in the engine, the group policy engine, processing the group policy files it's receiving. So the thing I've looked at very recently now was to look at these controls and say, okay, well, how effective are they? Do they prevent all these attacks? An important point, probably first of all, is actually that Microsoft went further than I expected. As I kind of implied earlier, I kind of expected the answer to be, okay, well, default configuration is vulnerable. There's a bunch of configuration options that aren't ideal by default, but you can improve them if you want a more secure network. And then I expected a fix for the SMB signing reversion. So yes, they did provide that fix, but they've gone further than that with this new security feature in hardened UNC paths. So, do hardened UNC paths work? Well, if they're configured correctly, of course, they are a pretty effective control. It's a good control to have. And effectively, most of what we've seen previously was via NTLM authentication when it was used to access an SMB. Effectively, if you configure this in line with their suggestions, then it won't use NTLM because NTLM can't satisfy the mutual authentication requirement. So what happens is you'll find that then Kerberos-enabled SMB access will be required because it wants to mutually authenticate the server it's talking to and provide packet sign-in within SMB traffic. So that effectively prevents the first exploit scenario we considered, if it's configured properly. MS15014, I did some basic testing of this. It seems to be effective. When I corrupted the response in a similar way to what I did previously, the requirement for SMB signing did not revert back to default, so that's good. That seems to be effective, and that prevents the second exploit scenario we were considering. So the other consideration is LDAP. So I mentioned, I come back to this previously. We saw that the default configuration earlier was to, even at the server level, not to require signing. But when I've looked into that, at least post-patch now, it seems to be that for group policy at least, if a client is accessing LDAP, then it will only allow Kerberos, it needs integrity protection, and so forth. So that seems to be pretty good from that perspective as well. Because my original idea for that was that, okay, if these new security features were put in place, but LDAP wasn't being signed properly, we could drop the requirement to apply the GPO that has the hardened UNC paths configured, and then next time it refreshes, it won't apply hardened UNC paths, and maybe we'll be back to square one again, and our old exploit would work. But that's not the case. What I saw with LDAP was good. But what about the third scenario we considered, the user settings exploit? Now, there was nothing in the bulletins and TechNet articles that I saw that really specifically addressed this issue. But the fact that it would require Kerberos if you've configured hardened UNC paths would prevent the specific technique that I showed before, because that was redirecting to our own SMB server. It was relying on NTLM authentication, relying on the fact that SMB signing can be calculated using a key derived from the user's password. If we use hardened C and UNC paths correctly, the fact that we won't use NTLM means that we can't actually authenticate ourselves to the client with our own malicious SMB server. We don't have the necessary keys to actually prove our identity to the client. And we won't be able to sign messages either, as when it's using Kerberos for SMB, the SMB signature key is not a simple derivation of the user password. It's based on all the Kerberos packets that have been exchanged prior to that. So the question at this point is that enough? It has stopped the exact exploit scenario I showed before, but has it really addressed the underlying vulnerability? Well, when I started looking into this post-patch, I found that the user account, user password effectively was what was still being used for accessing LDAP and SMB for user settings. So the question then became, well, is there a way to exploit that, or is just Kerberos going to prevent this whole thing? My question was, if we observe enough Kerberos traffic, does that give us what we need, or is it just not viable? So let's look at how Kerberos works. This is a fairly simplified example of it, but fits nicely on one slide. The first thing that happens is the domain member will send an ASREC message to the Kerberos service on the domain controller. And for that, it's saying, okay, I want a ticket granting ticket. And then the server will send a reply saying, yeah, okay, well, here's your ticket granting ticket, and here's an encrypted session key for us to communicate in future. And that's encrypted with something that's effectively derived from the user's password. So they're then able to decrypt that, and they've got their session key for communicating with Kerberos in future. Then, when the client wants to talk to the SMB server, it says to the Kerberos service, okay, well, here's the ticket granting ticket you gave me earlier. I want a service ticket to talk to SMB. And then the service goes, okay, well, yeah, here's your service ticket, and here's an encrypted service key. So you've got a service key that you can talk securely with that service, and that's encrypted with the session key from that it agreed with the service earlier. So then the main member goes, okay, great. Now I'm going to establish an SMB connection, and within that, I'm going to say, okay, it's an SMB service. Here's your service ticket. I want to access your service. And then the service will authenticate itself. because it'll be able to access the service key that the client knows now by decrypting the service ticket itself with its own shared key with the domain controller, at which point it will go, okay, yeah, the client sent me something that's valid, and I'm going to decide on a new subkey that we're going to use for signing communications from so forth, and I'm going to encrypt that with a service key that only the domain client knows. And I'll send it back. And at that point, we can carry on talking happily with knowing that we've both authenticated each other and we've now got a key we've agreed to sign the communications. So what happens if we try and decrypt these packets? Well, if we decrypt the first reply we get from the server, if we know the password, we know how to decrypt that. So we get the ticket, granting ticket, and then we decrypt the session key. So then we know the session key that the domain member's using. Then later, the domain member sends its request for the service ticket, and then the reply that comes back from the server has the session key, has the service key encrypted with the session key from before, which we know. So then we can decrypt that bit. And then later, when the actual request to SMB happens, when the reply comes back from the server there, it's got a signature, so it's got a key that it's then going to use, the subkey that it's then going to actually use for SMB signing, encrypted with a service key, which again, we know if we've been keeping track of everything, which means at that point, we know how to sign communications with SMB. So, although it's not exactly trivial, effectively, in principle, we should be able to, if we monitor the kerberos exchanges as well, and we're there from the beginning, and we keep track of all the necessary keys, then we can probably actually modify SMB responses on the fly when they happen later on in the communications if we've got the relevant keys from kerberos. Which means if everything happens as it did before, then we should effectively still be able to get system in this specific scenario where we've got a user account, a low privilege user account that we know the password for. So, demo time. So, just demonstrating here on the domain controller that we've got hardened UNC paths configured, and we've configured it in line with Microsoft's recommendations, and that's been pushed out to the domain member in question. So, we'll switch to our attacking machine now. We'll start up spoofing again, and we'll run a different script this time. And this time we're redirecting not just 139.445 communications, but also 88 for kerberos. And you can see there up here, it's trying to handle a kerberos packet that's already seen. It's not been able to do that successfully because it's not one it's able to decrypt at the moment, but it's seen it and tried to handle it. Anyway, that's just waiting. It's monitoring all the communications. So we just start our packet trace again, just so we can look at the traffic when we want to. We'll go back to Windows 7, and we'll log in as our low privileged user account. Okay, so that's logging in. Ignore that calc. That was just set as a wrong key. We'll go back to our attacking machine now. So at this point, we can see a whole bunch of stuff's happened there. And we can see what's happened is due to the kerberos exchange that's happened as a part of logging in, we've seen various different packets going along. We can see that one of the initial AS rep replies that's come back, we've managed to successfully decrypt with the user's password of password 1, and that's given us a session key. If you look down the list going on, we've got service ticket requests and so forth that have then been decrypted with session keys we've known about, and then subkeys that have been decrypted with service keys we've known about, and so forth. And it's effectively, if you see here, at some point we've detected a modifiable SMB registry read response, which we've been in a position to actually modify because we've got the relevant keys to recalculate the signature. So let's go back to our packet trace and see what that looks like. So we're just going to do a quick search or something. We'll get to a read response. So we see two read responses here. This is where we've got a custom little handler in Python that's redirecting these comms and handling the data that's going through them. So we see two things come back. One where the domain controller is sending it back to our handler, and then the second bit, which is what we then forward on from there back to the client. So we look at the first thing, what actually came back from the domain controller. We look through here. We'll see we've got a particular signature there. Now, if If we then look at the second response, which is what we ended up actually sending back, we'll notice that the signature's changed, and that's because we recalculated it. If we look at the data, you can see down here that we've got our own app-init DLL setting in there that we've decided to add in. So, if we go back to our handler, we'll find we've actually already got some shells because they should be running as the low-priv user account because obviously certain processes have started. But now if we do the same trick we did before, our desktop starts the new win logon sessions, and then again, we've got a couple of system shells as we did before. Okay, so a couple of caveats on this as well. User settings are not quite as flexible as computer settings in terms of default client-side extensions that are in place. So in this instance that I just showed you, I'd enabled a GPO that configured registry settings, and so that client-side extension applied, and it's that I took advantage of. That wouldn't be default unless that's been configured. It's something that people may commonly configure, but it's not necessarily a definite thing that's going to be in place always. So there's a slight caveat there. However, though I've not tested this, I'd mentioned previously that LDAP uses the user account as well, not the machine count for when it's querying for user settings. So I'm pretty sure that we should be able to use the exact same technique to modify LDAP responses too when that's using kerberos and, to negotiate its signing keys. And if that's the case, we could actually say whatever client-side extensions we want to apply for the GPO. So we could say, okay, well, apply this client-side extension because I want to use that. And then in that case, I'm pretty sure that with a bit more effort, you'd have the exploit in a place where it's actually going to affect a default configuration. So what's the conclusion here? Okay, prior to MS15011 and MS15014, as far as I'm aware, pretty much all enterprise Windows networks were vulnerable to this. So if you can intercept the traffic, then you could apply these attacks. Now, Microsoft have not added these new controls to XP in 2003. Now, obviously, XP was out of support anyway, but I think 2003 was still in support. But if you've got XP in 2003 systems, you can't really directly protect against these attacks anyway. But at least Vista 2008 onwards have got the new hardened UNC paths security feature there. But they're still vulnerable in default configuration. It's something you have to go out of your way to configure. So if you want to make sure you're protected against them, then you have to apply that configuration. Now, the new hardened UNC paths feature is really pretty cool. It's got ramifications outside of this as well. There's additionally cool things you could do. Maybe you could say, I want to make sure that communications with my file server are always encrypted. If you've got an environment that can support SMB3, you can configure that. And if you configure it securely, it does protect against the most serious of these attacks. But at the moment, at least, there are a couple of specific exploit scenarios that still apply and allow for forms of privilege escalation, like the last attack that we've seen, if you're in an instance where you know a particular user account for whatever reason. Okay, so at this point, any questions?
Yeah, it's very uncommon my voice isn't loud enough. The use of NLA, so 802.1x or something, to mitigate that initial sort of SMB hijacking, using any of these vectors, would that mitigate all classes of this vulnerability? So,
well, if you're talking about 802.1x, I mean, that's just the initial access to the network, right? So for an endpoint, like if I want to plug my laptop into a network for a port I find somewhere, yeah. I mean, if you're talking about rogue devices and you've got strong control against rogue devices, then I mean, yeah, that's an indirect control that would help against this. But if you have got a legitimate key for accessing that network, for example, then you should probably still be able to use ARP spoofing or something. Or if you have administrative control over a workstation, for example, then you may still be able to do that. So yeah, I mean, there are obviously environmental dependencies to consider.
So without, if you couldn't perform, say, ARP spoofing, are there other actual layer 2 vectors that you could use to get that man in the middle in?
Yeah, I mean, there's maybe DHCP hijacking, or there's a bunch of other interception techniques that may apply. So yeah, I mean, that is a dependency. It's only applicable in instances where you can intercept network traffic. So most commonly, a lot of those techniques are applicable to systems on the same subnet as you, but it's much more difficult to do that outside of your own subnet. So yeah, I mean, if you've got protections against ARP spoofing and protections against DHCP hijacking and other forms of interception, and you've got small subnets, for example, then obviously you limit that exposure a lot more. Whereas if you've got huge subnets for entire, big class Bs for entire buildings, and you don't have any traffic interception protection, then you're a lot more exposed.
Okay, so for the latest scenario, right, the user policy one that is still kind of works, and for that one specifically, how do you get the local system authority kind of level of privileges? I mean, you mentioned this client side extension that depends on the environment. I wasn't quite clear.
Sure. Okay. So I kind of demonstrated that vulnerability twice. So pre-patch, one way I'd exploited it, and post-patch with the complication of kerberos. In all instances, the actual kind of payload I put it in the end was to modify the app init DLL settings in the registry. So app init DLL settings, they define DLLs that should be loaded into every process when a process starts. So I just defined a DLL in a
Why
location
can you
I
write
controlled.
to that part? Like you mentioned that it's only possible with a certain extension.
Okay, so yeah, so I defined a setting in the user settings on the domain controller for there's literally a drop down where you can go and say, oh, add this registry setting. But it's part of user settings. Now that meant that an XML file that has a list of registry settings to apply would be pulled down by the client, and it's that file that I intercepted, modified, and recalculated the signature for to add my malicious registry setting to.
Right.
But that specific example would only apply when that client-side extension applies, which would only be if someone is making use of that functionality. But then what I went on to say after that is that even if that's not the case, for example, if I modify the LDAP communications, then I can probably go and specify that it should apply, and then I could use that in any default scenario. There are other client-side extensions as part of user settings that would be system equivalent as well. So there's user account and group membership settings you can configure too. But if you don't really do anything with user settings, by default, I believe you can only modify the user's own hive in terms of what's always pulled down, but I'd have to double check that.
All right. So if we assume that is enabled, do you consider it just a bug that probably needs to be fixed, that it can write to HKLM instead of the only user portions of the registry?
Well, I mean, I think it's functionality that's been defined, so I assume that Microsoft wants it to be that way. If anything, I would say that if there's a change to be made, it should be that when the machine is grabbing user settings, that it uses the machine account to authenticate and sign everything rather than the user's account. As long as that works, I would say that's the best protection, because then you don't, you assume that the machine account is secure. I don't know why it needs to use the user's own account to grab those settings. It should, well, maybe there's a reason that I don't know about, but for most of it, I would have thought that it can just use the machine account in principle.
All right, thanks.
Anyone? Anyone else? No? All right, Luke, thank you very much.